In this video, we're going to look at the radian and angles measured in radians, omega, which is the angular velocity, the velocity of an object moving in a circle, and finally, we'll derive the formula for centripetal acceleration. The circular arc length, radius, and radians. So the circular arc length, I call it S for displacement, but it's written as S or capital L for length or lowercase l in books. I use S. And if we have a circle with a radius, if the arc length S is equal to the radius in length, then the angle is 1 radian. That's your definition of a radian. And if the arc length is twice as long as the radius, the angle is 2 radians. If S is equal to 3r, then theta is 3 radians, and so on. But if the arc length S is equal to 2 pi r, or the circumference of the circle, then the angle in the whole circle is 6 odd, or 2 pi radians. So 6.283 radians is 360 degrees. And the angle in radians, that little c means radians, is the arc length in meters divided by the radius in meters. So this is important. Theta equals S over r. So angle ratios to convert between degrees and radians. Degrees over 360 is the same ratio as radians divided by 2 pi. So these are the conversions that I use. Degrees equals radians times 360 over 2 pi, or radians equals your amount of degrees times 2 pi over 360. But in maths books, it's written like this. So you can use either version. I prefer the versions in the green box because it makes more sense. So omega is the angular velocity, also known as angular frequency, in radians per second. Omega is the angle in a circle in radians divided by the period, big T, of one spin. So it's 2 pi over t, which is important to remember, and it's the rate of change of angle when we're spinning, and we're using uniform spin speeds. So omega is the angular velocity, how quickly we spin through an angle, or how much angle is spun through per second. That's why it's called the angular frequency as well. So we have a circle here with a mass on the edge, and we're going to spin. You can see it here, the period of rotation is 1 second. So omega is 2 pi radians over 1 second. So it's 2 pi radians per second. That's the angular velocity. Now we've slowed it down. So it's taken 2 seconds to go through 6.283 radians or 2 pi radians. So the angular velocity or angular frequency now is pi radians per second, just over 3 radians per second. And if we slow it down even more, now it's taken 7 seconds to spin through 2 pi radians. So omega is 2 pi over t. 2 pi radians divided by 7 seconds is just under 0.9 radians per second. So omega is always 2 pi over t, also equals 2 pi times the frequency in hertz, and it's in radians per second, so it's very important to remember that. Here's a mass orbiting or spinning around the center of a circle, love in life. And we're going to look at part of the spin, just a sector of the circle. We learned earlier that theta in radians is the arc length S divided by the radius r, and if S equals 2 pi r, theta is 2 pi radians. But if we draw a straight line connecting the edge of the circle instead of a curved arc, we can see that for small angles of theta, the length of the straight line L is approximately the same as the arc length s. This is called the small angle approximation, and it comes in handy for circular motion. So if we treat the bottom triangle as an approximate right-angled triangle, where the opposite side is approximately the arc length s and the adjacent and hypotenuse are the radius, then the sine of theta in radians, which is opposite over hypotenuse, is basically the same as the s over r ratio, which is theta. The same is true for tan theta, and this works for small theta values up to about 0.2 radians. So for small angles in radians, the arc length is roughly the straight line distance. With uniform circular motion, the speed of the moving object is always the same. It's only the direction of the velocity that changes. So the velocity is perpendicular to the radius. Let's find the change in velocity delta v so we can see the direction of the acceleration of the object. The change in velocity is v2 minus v1, or v2 plus minus v1. So we take the final velocity vector v2, subtract the initial velocity vector v1, and the resultant vector is the change in velocity delta v, or dv. So dv equals v2 take away v1. The change of velocity is towards the center of rotation, and the change of velocity over time is acceleration. So the centripetal acceleration is towards the center of rotation, and this is y. To find the formula for centripetal acceleration, we look at the two previous triangles. On the left is the velocity vector triangle, and on the right is the radians equals arc length over radius triangle. And they are mathematically similar, which means they share the same angles and length ratios. You can see that dv over v equals the arc length s divided by the radius because they're similar. So dv over v is s over r. But we also know that the arc distance traveled s equals velocity times time, because distance is velocity times time. And if we substitute velocity times time for s in equation A, we get dv over v equals v dt over r. And then with a bit of rearranging, that gives us dv over dt equals v squared over r. But dv over dt is the rate of change of velocity, and that is acceleration. So the centripetal acceleration, A, is v squared over r in meters per second squared. So that's where that comes from.